Good morning, everyone. I'm just looking here to wrap up chapters 15 and 16 material. Today we'll be going over polyprotic acids, buffers, common ion effect, indicators, and complex ions and solubility products. The central theme that you're going to see here throughout the lecture is the common ion effect. Okay, so let's first start off with polyprotic acids. Right now, the only training you've had is just in monoprotic acids. So these are acids with 2 or 3 protic hydrogens. So in other words, they can let go of multiple hydrogens, sort of like what you see right here. So on the left, this is phosphoric acid. Losing one hydrogen or proton, it's going to have one negative charge. So presumably there's going to have some kind of counterbalance there. Okay. And then, so this would be the conjugate base of phosphoric acid. This would be the conjugate base of that one missing hydrogen right here. So in other words, there are 2 missing for this anion, and then a total of 3 missing for this anion. So these are all conjugate bases of one another. Now, so that is to say that polyprotic acids have 2 or 3 protic hydrogens, so therefore they can have 2 or 3 different Ka values. Okay. So take phosphoric acid, which is the conjugate base of, let's just say, NaH2PO4. So typically, phosphoric acid is represented as H3PO4. So in other words, in lieu of having one of those hydrogens to count, the first one that's going to be missing is going to be replaced with a sodium cation. Okay. Okay, so let's look at an example here. An example that's actually kind of been expensive on my end, and I'll get to that in a minute. So oxalic acid, so I have a cat, and I have 2 cats, but one of them is actually prone to form crystals in his urine. So when you have oxalate, which is going to be the second conjugate base of oxalic acid in urine or pH, low pH, may have mono and dibasic forms. Okay, so the dibasic form is actually going to form a crystal with magnesium. Okay, so magnesium oxalate is going to be an insoluble complex, or poor non-electrolyte that basically isn't going to form any ions in solution. So what that'll do is actually trap in my boy's urethra, and it's very painful for him, and he has to get stuff flushed out. So I have to buy expensive food to make sure that he doesn't do that. So anyway, all right, let's get into a problem here. So 15.72 on page 719. What is the pH of oxalic acid at 0.0288 molar? I'll give you a couple minutes to try to figure that out. Pay attention to the pKa values that are in the back of the text and convert those over from pKa to Ka. Okay. And remember that this is just the negative log of Ka. So do that conversion first, and notice that there's not just one Ka value, but there's also Ka2 as well. Okay. Okay, so let's resume here. We have our first fully protonated species that has a pKa of 1.23. So converting that into the 10 to the minus pKa, that's going to give you a Ka1 of 5.89 times 10 to the minus 2. Okay, so that's Ka for the first deprotonation. Now for the second, it's a little bit higher in magnitude, pKa of 4.19, and that Ka value, if you were to take this times 10, or take a negative of this, so in other words, if you were to take this 10 to the negative 4.19, you're going to get this value. Okay, so in other words, 10 to the minus pKa is going to give you Ka. Okay, so 6.46 times 10 to the minus 5, so it's much lower in magnitude than you see for Ka1. All right, now only the first pK is relevant, since Ka is 1 is much smaller, or is much greater than Ka2. Okay, so in other words, remember, if we were just to look at this one particular dissociation constant, it's going to be pretty marginal relative to the actual concentration that we have of this acid. Okay, so a Rice chart is needed for this question. So we're going to start off with presumably 0.0288 molar oxalic acid. We have 0 amount of initial oxalate, or monooxalate, I guess, and then 0 of H+. Now, when we undergo a change, we're going to have a minus, so it has to come from somewhere, right? So minus X, and you're going to generate proportional amounts of the conjugate base form as well as H+. Okay, and then at equilibrium, of course, you're just going to take the difference, right? So X minus 0 is going to give you X. X minus 0 is going to give you X down here. And then you have 0.0228 minus X, right? So the amount that you've lost, or where these two species came from, which is, again, the conjugate acid form. Okay, so thus the Ka is going to be equal to, if we were to look at our equilibrium expression, right? So this is going to be X squared, so X times X on the top, and then on the bottom we're going to have our reactants, quote unquote. Okay, so 0.0288 minus X on the bottom, on the denominator. If we multiply both sides, we're going to get this now on the right hand side. So it's going to be negative 589 times 10 to the minus 2 X, right? So that X factor multiplies it, and then we're going to take 0.0288 and the product of 5.89 times 10 to the minus 2 to give us our C value for our quadratic. Okay, so now that we have all that set up, right? Now all we have to do is simply move everything onto the other side to equal it to 0. Okay, so essentially you're going to add 5.89 times 10 to the minus 2x to both sides. Okay, so that's where it's going to show up here, and then you're going to subtract 1.7 times 10 to the minus 3 to cross this off, so the right side is going to be, again, 0. So negative 1.70 times 10 to the minus 3. Plug those three A, B, C coefficients. This is going to be 1. This is going to be 5.89 times 10 to the minus 2. And this is going to be negative 1.70 times 10 to the minus 3. Plug that into a calculator or into some kind of quadratic calculator. And X is going to spit out a positive number of 0.0212. Okay, so that is going to be your X value. Remember that H plus at equilibrium is going to be X. So in other words, the H plus concentration is going to be X. So the pH is going to be equal to the negative log of H plus, as you know by now. Okay, and then taking negative log of 0.0212 molar is going to give you 1.67 as your result for pH. So 1.67 is going to be the pH reading of 0.0288 molar oxalic acid. Okay, so let's re-examine Le Chatelier's principle for a minute. So let's think about carbonic acid, which is H2CO3, and potassium carbonate, do they actually have common ions among them? And the answer is yes, they have one particular common ion, and that's going to be the carbonate. Right? So CO3 2 minus. If you were to imagine its Lewis structure, it would look something like this. Okay. So that's going to be a stable anion, polyatomic anion, that has some kind of resonance stability to it. Okay. So in other words, these negative charges can kind of flip up to the next oxygen, do-si-do around, and just, essentially gather around the wagon, if you will, to stabilize that particular divalent charge. Okay, presumably you're going to have some counter ions like K plus, H plus, whatever, right, to stabilize that charge. Okay, so how is that actually going to affect the acid-base equilibria? Well, recall that Ka is going to be equal to H plus times the conjugate base over the conjugate acid. So in other words, if you add more of A minus, let's say, what's that going to do to the equilibrium? It's going to shift back down to reactants, right, or your conjugate acid. Okay, so let's see if this will affect the pH of the solution. Okay, so now we're looking at the next chapter, so problem 16.22 on page 764. Why don't you take a couple of minutes to see if you can come up with what that question asks. Okay, and we're back. Now, problem 16.22 on page 764 asks, what is the pH of a buffer that is 0.100 molar methylamine and 0.175 molar methylammonium chloride? Okay, so now a buffer is simply a conjugate acid-base pair system. So if you want to think about this from a biological perspective, your blood is actually a means of a buffer. Okay, so it's basically a way of regulating the pH of a particular system. So unless it goes over capacity, or in other words, if you add so many H plus ions, then it's going to break that buffering. But the buffer is essentially supposed to stabilize a particular pH environment based on what kind of conjugate acid and base proportions that you have in a particular system. Okay, so the equation is going to go like so. Methylamine is going to behave as a weak base, so it's going to pick up that H plus from presumably HCl, since you're going to be forming that salt. Okay, so there's going to be that Cl minus. It's going to stabilize that charge of this methyl ammonium cation. Okay, so that is the proton transfer. Now, if we think of pKb, we can always relate that back to pKa with that. Remember that 14 is going to be equal to pH and pOH. pOH and pH and pKa and pKb are very similar in terms of relating to Kw. Okay, so to solve for pKa, because eventually we're going to have to know that to determine how much of HA is going to be formed, right, and how much of A minus is going to be there in ionic form. Okay, so 14 minus the pKb is going to give you your pKa. So 14 minus 3.36 is going to give you 10.64. Okay, so now we have that data, or we have that piece of information. Okay, so now if we're looking to solve for the pH, we simply have to plug in that pKa value right here. And then we have plus the log of the conjugate base over the conjugate acid form. Okay, so just because you don't see H plus here, or you don't, this is effectively H plus, right? or HA if it were. So A minus HA. Okay. Now, this is actually important because this can determine whether or not you can have some kind of solid species falling out of an aqueous solution. So actually, I when I was in or looking to apply to graduate school, I had informed my employer at the time, which will remain nameless, that in order to not have crystals come out of solution in an aqueous medium, you'd want to buffer it to make sure that none of the crystals are going to form. Sort of like what happened with my poor cat, right? So because whatever their particular aqueous solution was that they were going to put into liquid foundation makeup, if it forms crystals over time, that's going to be a no-no, because some poor girl is going to want to apply that stuff to their skin, and then you're going to have lawsuits and things like that. So in other words, I told them in their formulation to basically do an adjustment of a pKa, and they actually listened. So that was pretty cool. All right, now back to just sort of a war story, if you will. Now, we have our pKa value. We're looking to solve for our pH. So based on this balance of conjugate base to conjugate acid, that should determine what the actual pKa is, right? So if this were 1 and 1, this would actually just go out to be 0, and then your pH would be equal to 10.64. Okay, but since these are offset a little bit, right? So you have 0.100 molar of your conjugate base and 0.175 molar of your conjugate acid, it's going to be a little bit more in the favor of NH3. So in other words, your H plus concentration is going to be slightly higher than if we're quote-unquote neutral among those two species. Okay, so in other words, that's going to drive the actual pH down, right? So we take the log of 1.1 over 0.175. That's going to give you negative 0.243. So remember that if it's a decimal point and it's less than 1, then that means it's most likely going to spit out a negative answer for you. Okay, so 10.64, again, that's the pKa, plus negative 0.243 is going to give you an overall pH of 10.4. So it's only adjusted the pH units about 0.2. Okay. Now, we will look at another example here on page 764 again. So this is problem 16.30. So notice here how they already gave you the concentrations. Now they're going to give you the actual masses, and you have to figure out the fixed amounts in that particular solution. So again, problem 16.30 on page 764. I'll give you guys about 5 minutes to work on that, and then we'll look at the answer. Okay. So question states, what masses of ethylamine and ethyl ammonium chloride do you need to buffer at a pH of 10.5 if the total concentration of both components is 0.250 molar? So that means that's the total amount or concentration of both ions, right? So ethylamine itself, and then ethyl ammonium chloride, which is going to be its conjugate acid. Okay, so the first thing we're going to do is take the Henderson-Hasselbalch equation like we had in the previous example. So that means pH is equal to pKa plus log of ethylamine concentration on the top over ethyl ammonium chloride on the bottom. Okay, so the pH minus pKa is going to be equal to that particular term. So in other words, what I did was I subtracted both sides by pKa. Okay, so the next step is in order to solve for the ratio of A minus to HA, or more generically it's conjugate base to conjugate acid. It's going to be 1 times 10 to the pH minus pKa. So you need to make a difference of that. Way to solve for the pKa, just like what we did with the previous example, is take the pKb rather, and subtract that from 14. So it's going to be 10.81. Okay. So 10.50, which is our target buffer pH, 10.50 minus 10.81. And you take that to the 10 to the x, and that should give you exactly 0.49. Okay, so that means A minus over HA. That's the ratio. So that means for every one of these, you're going to have half of that. Okay, in terms of breakdown. Okay, so in other words, A minus concentration is going to be equal to HA concentration times 0.49. Okay, so now we have to incorporate that all into 0.250 molar, which is, again, what the components are going to be 0.25 molar in total. So let's do this and flip it over to the back page here that I have. Okay, so now we're going to work with 0.25 molar. Now, notice how I put 1.49 times HA. Okay? Now, the reason I do that is that I'm simplifying, so we're assuming that, you know, there's going to be one equivalent of this and then half of an equivalent from the A minus. Okay, so that's why I have this as 1.49 as opposed to just 0.49. Okay, so with that, if we're going with a total amount of 0.25 molar, we divide it by 1.49, and that should give us our amount of conjugate acid that's actually present, right? So you can just double check this work if you wish. So 0.168 molar of HA, or ethyl ammonium chloride. Okay. So with all that, since we're thankfully working with 1.00 liters, simply to solve for the mass of each component, we're going to take the volume, multiply it, the particular component's molarity, times the actual molecular weight of that component. Okay, so for the conjugate acid, we're going to take 1.00 liters, which is what we're working with. The 0.168 mole or molar value that I calculated above, and then so your liters are going to cancel out. Okay, and then your moles of HA are going to cancel out, and then you're just going to be left with grams of HA or grams of ethyl ammonium chloride. Okay, so that's going to leave you with 13.7 grams for that particular component. Now, looking at the conjugate base, so we're going to deal with 1 liter once again. Now we have to take the difference between that 0.250 molar total concentration that we're working with, and take away the part that's in conjugate acid form. So taking away 0.168 amounts or moles of A minus, that's going to leave you with a difference of 0.082 mole of A minus per liter. Okay. So in other words, liters are going to cancel out again, moles of A minus are going to cancel out again, and you're just going to be left with grams of A minus, or 3.70 grams of ethylamine. Okay. Okay, so let's think back and think about what kind of volumetric analysis we're going to employ or incorporate to figure out exactly what kind of concentrations we're dealing with. So I'm going to give you a scenario here. Suppose an acid was neutralized where all of its H plus ions would be picked up by a stronger base than its conjugate base, right? So in other words, something has to be more fitted to be an acid, one needs to be more fitted to be a base, okay, in order to have an effective transfer. How can we really tell, seeing as different acids have different pKa values? So it's nothing that you can see with the naked eye, right? There needs to be something that's there to indicate, no pun intended, that you've had a change in H plus ions. Okay, so or a change in pH as a result. So you can take a look at some of the different indicators that are used in Figure 16-5 in your text. Okay, so just a few of the examples that I'm going to bring up here. So let's say one is methyl orange. So it has a range of pH 3 to 5. So when it raises pH, it's going to go from red to yellow. So if you're starting at a low pH, in other words, a pH of less than 3, it's going to show up as a pretty much bright red. But as you start adding more base to it, it's going to go from red to yellow. Okay, so another example here is bromethymol blue, which is something I've used. It's a little tricky to get from yellow to green to blue. Sometimes things are a little bit, how you would say, sensitive, a little easy to overshoot. Now that pH range is from 6 to 7.5. Sorry if you can't read that very descriptively, but essentially it's going yellow to green to blue as you increase the pH. So those actual indicators, that green should tell you it's going to be somewhere, it's going to be pretty much right around pH 7. Okay. And then phenolphthalein, which is more ubiquitous use, is going to be nearest to where a strong base is going to, let's say, titrate a weak acid. So colorless to pink to purple. Okay, so you might have done an experiment last semester where you were looking at titrating, let's say, a weak acid like vinegar with NaOH, which was standardized. So you're going to go from colorless to pink to purple, and that pH range is going to be between 8 to 10. So when you're up there to right around 10, that's where you're going to have this pretty strong sort of fuchsia, blinding color, okay? Or really sort of like a deep hot pink, if you will. So which one of these indicators would be appropriate for titrating ammonium chloride? And I'll let you kind of ponder on that as we move along and look at some titration curves in the next slide. Okay, so let's take a look at some of these titration curves here that I have sort of color indicated, if you will, to spot the differences among strong and weak acids and weak bases. Okay, so the pH versus volume. So pH is going to be the y-axis, volume is going to be the x-axis. Okay, notice how I have a neutrality point right there at pH 7. So this is kind of to try to give you the idea of, where you're going to see an endpoint. So the endpoint is essentially an inflection point. So that's where basically the change in pH is going to be at a maximum. Okay, so let's say right here is an inflection point, right? So it's right there in the middle. If you were to just say, kind of dash your top and bottom sort of places where things drop out. Now notice we're going from 0 to increasing concentration. So we're starting at basic conditions and we're going down into, as you add more titrant, into acidic conditions. So above 7.0 in magnitude, less than 7.0 in magnitude. So in other words, you would be titrating a strong base with a strong acid. Okay, so strong base, analyte, strong acid, titrant. All right. Now let's look at the next example here. So we're starting out at slightly basic, just above 7.0, and dropping down to a really low pH. So again, this is going to be pH here. Okay. So we're starting out with a weakly basic. We're basically bringing it down to a really low pH. So In other words, this is going to be a weak base for an analyte. And then you're going to use a strong acid for a titrant. And by the way, at any point in this video, if you want to just pause and take a look at some of the other future examples that I'm going to be going over, and give them a shot and see how you do, without my guidance, you're more than welcome to. This is already free to, print off and for your perusal. Okay, so let's look now at the next example here. So pH 7. So now we're starting off with an analyte that's slightly acidic, right? We'll eyeball it at maybe 5 or 4. Okay, and then we're adding some kind of titrant to raise the solution, and then pH is going to be way up above at the top as you reach a neutral point. So, in other words, here's where the inflection lies in between where you started out with and where you're basically going to flatline there toward the end. Okay, so that's going to be the inflection or end point. So that means that's going to be, in other words, a perfect match of A minus, let's say, to H plus concentration. So they're going to be equal in concentrations. Okay. Now, that's not to say that they're always going to be at pH 7, because in this particular instance, you're going to have a weak acid as an analyte and a strong base as a titrant. Okay, and then the last one here. So we're starting off again somewhere in the neighborhood of pH 5, pH 4, adding some titrant. Things kind of move along, and it's going to be slightly basic as you add more titrant. So in other words, the inflection point should be right there at pH 7. Okay, so that means that we're basically going to be titrating a weak acid analyte with a weak base titrant. Okay. So, was I to spare you from mathematical hell? Don't count on it. All right, so let's look at some titration calculations. All right, so with incorporating indicators and woo-wee, let's get going. All right, so problem 16.54 on page 765 states, what color would red cabbage juice have at the equivalence point when 25 ml of a 0.1 molar acetic acid is titrated with 1.1 molar NaOH? How much titrant is required, and what will be the pH at equivalence / neutralization? Okay, so I was kind of tricking you a little bit, because really you could do the calculation, but it's not entirely necessary. Now, if you take 25 ml of, let's say, a 0.1 molar acetic acid solution, that's going to be a low enough concentration to where pretty much all of that acetic acid is going to ionize enough to where something like a strong base is just going to sponge it right up, presumably with the equal amounts of volume. Okay, so how much titrant is required? Well, I'll let you be the judge of that. But what will the pH equivalence / neutralization be? That's going to be just above pH, let's say pH 9, pH 8. So in other words, this red cabbage juice could be an indicator that could be, let's say equivalent to something like phenolphthalein, right? So phenolphthalein is going to look at a particular range at anywhere between pH 8 and pH 10, so weakly basic, okay? So in other words, no calculation required. Like no jacket required, right? Okay, so that would look like if you were to do your, what do you call that? Titration curve. It should look something like this, really. Right? So you're taking a weak acid, like acetic acid, and you're titrating it with a strong base like NaOH. Okay, so that equivalence point is going to be somewhere just north of pH 7. Okay. Okay, so let's look now at a different topic. So this is going to be shifting gears to solubility products. So if you're a little bit shaky on solubility rules, you can revisit that in Chapter 8, page 336, and you can kind of look at some of those textbook examples of things that are insoluble. Furthermore, you can look into the appendix and look at some of the KSP values that you'll find. Okay, so let's just go over a little bit of theory here before we jump into this. Let's consider calcium oxalate. So calcium oxalate is going to be similar to the oxalate that blocks up my boys' urethra and causes them pain. So how many particles would you expect to form here? So you have calcium, which calcium is going to be 2+ in its oxidized form, and then you're going to have oxalate, which is going to actually have 2-. So in other words, you're going to break this up into 2 charged particles. Okay. So in other words, what you're going to see is for your KSP is going to be equal to your concentration of Ca2+ times the concentration of oxalate. Okay. Now, the solubility product, or KSP, is simply the constant at which a concentration of ions, negative, positive, polyatomic, whatever, is multiplied. So remember, the solids aren't expressed in an equilibrium expression, so that means you're not going to see anything below here, where it says, this in this concentrated form at the bottom. It's solid. It's going to fall out of solution. Okay. So let's now relate solubility itself to see what the solubility product is. Now, if you take a look on problem 16.96 on page 766, the question states if 0.16 grams of calcium hydroxide or lime dissolves in 0.100 liters of water, what is the KSP value for calcium hydroxide? Okay, so if we were to write the KSP for this particular ionic compound, we would put Ca2+ in brackets for its concentration multiplied by OH minus, and then that would be squared, remember? Because there's 2 equivalents of hydroxide. Okay, so in other words, what we want to do here is figure out what molarity we have in 0.1 liters that is going to give us our KSP value. So in other words, we're going to have 1 count of amounts from Ca+, and then 2 amounts of OH. So why don't you guys compute the molarity, and then we'll figure out what the KSP value is this. I'll give you 3 minutes for this. Pause. Okay, so coming back to solve for our KSP, first thing we want to do is solve the molarity. So 0.160 grams of calcium hydroxide converted to moles is going to be 2.16 times 10 to the minus 3 moles of calcium hydroxide. You're going to be using the molecular weight for that, okay, to do that conversion. So then if we take that amount and then we divide it by the 0.1 liters or 100 ml that it's dissolved in, that's going to give us 2.16 times 10 to the minus 2 molarity of calcium hydroxide. So if we want to solve for the KSP, we actually have to take the concentrations of each one of these ions, right, and multiply them all out. So in other words, 1 concentration here, 2 concentrations, 3 concentrations. So that means 2.16 times 10 to the minus 2 molar cubed. So that's going to leave us with 1.01 times 10 to the minus 5. Okay, remember that KSP is going to be assumed to be unitless. Okay. All right, on to the next problem here. So it's a similar kind of example here. If 2.67 times 10 to the minus 3 grams of barium sulfate is left over from 1 liter of water used to wash a much greater amount of it, what is the KSP of barium sulfate? Okay, so first things first, to solve for the KSP, I'm simply going to take KSP equal to the concentration of barium. Okay, so this is a pretty textbook example in terms of something that's insoluble, right? Barium. So most of these salts are going to be highly insoluble. Okay? So 4,2 minus for the other ion, and we don't have any coefficients. So in other words, we don't have to multiply anything out or use any exponents. Okay, so 2.67 times 10 to the minus 3 grams is left over out of evaporated 1 liter of solution that sponged it up. Let's convert this into moles. Okay. Okay, so now that we have our conversion factor, our molecular weight, 2.67 times 10 to the minus 3 grams of barium sulfate converted over into moles, that's going to leave you with 1.14 times 10 to the minus 5 moles of barium sulfate. Okay, so now the KSP value that you would want to compute is basically taking the ion concentration, so there's 1 barium to 1 sulfate. So in other words, you would take this particular value and square it. So, x to the 1, x to the 1 here, so x squared. So 1.14 times 10 to the minus 5 molar squared is going to leave you with 1.31 times 10 to the minus 10. Okay, so let's wear the shoe on the other foot and calculate the solubility of a compound from its known KSP. Okay, so this is problem 16.99 on page 766. It says, what is the solubility of calcite, or calcium carbonate, in grams per milliliter at a temperature at which its KSP is 9.9 times 10 to the minus 9. So KSP is going to be equal to calcium 2 plus times carbonate concentration, and that's going to be 9.9 times 10 to the minus 9. Okay, so in other words, if you wanted to solve for the actual concentration of either of these ions, what you would do is just simply square it, because you have 1 exponent here, 1 exponent here. So in other words, to solve for Ca plus, 2 plus, right, or CO3 2 minus, or really, if we think about it, calcium carbonate itself that's in solution, right? That's going to be the square root, I'm going to put a 2 here to make sure it's a square root of KSP. So in other words, this is going to be the concentration. I know that the particular question was asking for grams per milliliter. So grams per milliliter is the solubility. Okay. So why don't you guys take a couple of minutes and figure out what that gram per ml solubility will be. All right, so now that we got our KSP squared, we get 9.9 times 10 to the minus 5 molar or moles of calcium chloride or carbonate per liter. Okay, so now we take 9.9 times 10 to the minus 5. We take that molecular weight of calcium carbonate over here, convert this back into grams. So that means moles of calcium carbonate are going to cancel out. And then liters are going to cancel out as well. And we're going to have milliliters on the bottom. Okay? So in other words, we're going to express everything in grams per mil. So it's going to be 9.9 times 10 to the minus 6 grams of calcium carbonate per ml. Okay, so very low solubility. Okay, so let's take a look at this because particular cations, so say Mg2+, barium 2+, lead 2+, etc., may have drastically different solubility with different paired anions. Okay, so in other words, you have to combine these two in order to make a neutral compound. So let's compare calcium 2+ and Na+, and NO3- and F- for those solutions with calcium fluoride. Okay, so calcium fluoride in the solid state, we need to figure out which one of these solutions that I'm going to have listed here are least to most soluble. So in other words, how much calcium fluoride can I dump into each one of these? So take a look at the molar concentrations of each one of these solutions and see. You don't have to calculate exactly how much is going to go in, but you at least want to eyeball or estimate which one of these compounds or which one of these ionic solutions is going to be most dissolve this calcium fluoride. So why don't you take a couple of minutes, take a look at the KSP of solubility of calcium fluoride and some of these other cations and anions that are paired up and see which one would make things most soluble. Again, take a look and think of the common ion effect and Le Chatelier's principle when you do this. So I'll give you a couple minutes for that. Pause. All right, so to kind of revisit, calcium fluoride is going to be so soluble in deionized water, right? So there's no other ions to, matching ions or common ions to be in place there, and that's going to, maximize the solubility of calcium fluoride. However, per Le Chatelier's principle, per the common ion effect, if you have a common ion in a particular concentration, the higher the concentration, the less likely that particular solid is going to dissolve, right? So if we take, for instance, calcium nitrate, which is fully soluble in water, we're going to have 0.1 molar calcium, right? All right, and then for B, we're going to have 0.01 molar fluorine. Okay, so sodium fluoride. Now we have that reduced by tenfold, so that's going to be 0.001 molar F minus. Sort of like this weather is F minus right now. All right, and then even higher concentration of 0.10 molar calcium plus. Okay? So in other words, if we were really looking at amounts, right? Now, if we were to look at, let's say, 0.01 molar of of calcium fluoride, only so much of that is going to go into into sodium fluoride in this particular concentration. Right? So, in other words, between its A and B solutions, that is going to be more soluble in the 0.01 molar fluoride anion, okay, as opposed to calcium 2 plus, because you only need one equivalent here from the calcium fluoride. You need two equivalents of F minus in order to dissolve it. So in other words, the one that's going to be most freely to dissolve is the lowest concentration of common ion here. So in other words, this common anion of 0.001 molar F minus is going to be where calcium fluoride is going to be most soluble. So C is going to be highest. That's undisputed. Followed by B, which is going to be second highest. Then we're going to have between A and D, notice there's a 10-fold difference in Ca plus concentration. So that means we're going to put A right here. And then, of course, least soluble is going to be D. All right. So again, common ion effect, Le Chatelier's principle is really going to tell you just how much of calcium fluoride is going to go into each one of these solutions, just theoretically. Okay, so let's summarize and put some of this into context here. So which compound precipitates first? Well, that depends on the ion product or cation, and what coefficient it has, as well as the anion and what kind of coefficient it has in a particular ionic substance. So this is pretty much the same as the quotient that we were looking at with respect to KEQ, only this time it's the solubility product, or KSP, right? We're not factoring in any type of solids that are formed. So if the ion product, or KSP, the ion product is going to be essentially your quotient of KSP. If it's greater than KSP, then that means that what? That means that it's going to be dilute or concentrated. So I'll let you think about that. If the ion product is equal to the KSP, then things are actually saturated. Okay? But if the ion product is less than KSP, then, okay, so I'll give you a minute to think about that, and then I'll provide the answer. Okay, so to review, if the ion product is greater than KSP, then the solution is supersaturated. In other words, you're going to form some insoluble salt, right, or insoluble ionic compound that's going to precipitate out. Okay, so in other words, you're going to have some solids, and you're going to have your quote-unquote saturated solution there. So if the ion product is actually less than KSP, then that means that solution is actually dilute. Okay, so that means it hasn't reached that critical mass in where things actually precipitate and bloom out. Okay, so let's look at problem 16.109 on page 767. So this is basically what is referred to as ion scavenging. So this is used in water treatment facilities to see how much calcium hardness or what kind of lead content or whatever have you is present in water, right? Even at low concentrations. Okay, so let's take this particular example as 16.109. Let's just deal with A. This is on page 767. So it says a solution is 0.10 molar in both Br minus and SO42 minus concentration. A 0.25 molar solution of lead nitrate is used to titrate the other solutions of Br minus and SO42 minus. And it says which precipitate will form first. Okay, so we have two different possible precipitates we can form here. Quite an alliteration there. Okay, so we're going to have lead bromide, or PBr2. And then, so we'll need the KSP for that. And then we'll also need the KSP for lead sulfate. Okay, so these are mostly insoluble salts. We'll come back with KSP, and then we'll figure out which one of these ions will form first. And we'll see if we can take a wild guess on that. So we'll pause, take a few minutes, do some calculations, and see what you come up with. Okay, so remember, if the ion product is greater than KSP, the solution is supersaturated. If it's equal to KSP, then saturated. If it's less than KSP, solution is dilute. Now, we have 0.01 molar in both Br minus and SO42 minus. The question asks if you add a 0.25 molar solution of lead nitrate to titrate the other solutions of bromine and SO42 minus, which precipitate will form first. Okay, so in other words, we need to solve for the concentration of lead that would amount to forming first. But really what you need to do is test, well, we have lead bromide, we have lead sulfate that are going to form, undoubtedly, right, because it's a solubility product. That KSP for each one, for lead bromide, it's 6.6 times 10 to the minus 6. For lead sulfate, it's 1.8 times 10 to the minus 8. Okay, so the smallest KSP is going to be the one that's going to form first, right? Because you just have two particles that could combine to form this solid here, whereas you have three for lead bromide. Okay, so lead 2 plus is required. So in other words, the less lead that's required or needed to form a precipitate, that means that precipitate will form first. Okay, so if you have Br minus, which will precipitate at where lead concentration is going to be equal to the KSP divided by Br minus squared. So that means, remember, we have that starting concentration of 0.010 molar. We divide that by 1. So we divide the KSP by 0.010 molar squared. That's going to give you 6.6 times 10 to the minus 2 molar of lead that's going to form that precipitate. Okay. Now, if we take a look at our sulfate ion, now remember, this is pretty much the threshold that we're working with. So after this concentration, as that concentration continues to increase for lead, that's when we're going to start to actually find some finite amount of lead bromide that will come out of solution. Okay, or this is where the lead bromide actually starts to form. Okay, so now when we look at SO42 minus, now that we're going to take that initial concentration of lead, so that's pretty much the floor for lead sulfate formation. So we take that particular KSP value and divide it by lead 2 plus. So it's going to be 1.8 times 10 to the minus 8 divided by 6.6 times 10 to the minus 2. And that's going to give you 2.7 times 10 to the minus 7 molar lead plus 2 plus concentration. Okay. All right. Now on to the last topic for exam 2. This is going to be complex ion equilibria. So you might recall this back during the experiment where you were looking to establish the equilibrium constant experiment. So that involves the formation of a complex with metals, which are Lewis acids, and then ligands, which are Lewis bases. So these metals have an electron deficiency, and the ligands are lending electron pairs over to stabilize those metals. Okay, so there's a formation constant. This is usually high, so bear that in mind. So that K of formation is going to be the complex ion, so that could be positive or negative on the top, divided by the metal concentration, divided by the ligand concentration to the n power. So usually there's going to be one or more ligands that are going to participate in the overall complex. So to go in the reverse, so that's the K of formation. If this is going to be really high. That means that complex is going to be high in concentration, and the free metal and the free ligands are going to be low in concentration as a result. Okay. So the inverse is the dissociation constant. So is what you typically think of when you think of Ka or Kb. Okay, so in other words, this is pretty much flipped around, or the inverse, right? So Kf to the minus 1. Okay, so in this last example, which is going to be painfully long, we'll do it anyway, because there's still some theory to kind of hash out here. Okay, so problem 16.72 on page 765. If 1 ml of 0.100 molar silver nitrate, which is going to be a strong electrolyte, 1.00 mils of 0.1 molar sodium bromide, and 1 ml of 0.100 molar sodium cyanide are diluted with deionized water to 250 mils of a total volume, will any precipitate form? Okay, so here's what this is what the battle is going to be about. It's going to be about how much silver actually forms AgBr, or silver bromide, and how much actually forms this particular complex ion here. So notice that KSP is 5.4 times 10 to the minus 13, so that means abysmally low. And then the K of formation for the cyano complex. So this is silver with 2 equivalents of cyano to give you a negative charge. That's 1.0 times 10 to the 21. So in total orders of magnitude, we're looking at what, 34 in difference? So it's pretty high. Okay, so in other words, where will the Ag plus go? Will it form a complex, or will it form this sodium bromide product? Or sorry, not sodium bromide, silver bromide product. Okay, so I'll give you a few minutes to hammer that out, and then we will go over the long-winded answer. So I'll give you 10. Why don't you pause and work with that, and then we'll go from there. Okay, to wrap things up, the first thing that we're going to need for this problem is amounts of ions and then the concentration. Okay, so remember, we're putting mLs of each of these concentrations into an overall mixture. Okay, so the first one we're going to use is we're going to figure out how much silver is going to be needed to essentially make the amount of silver cyanide complex that we're going to form. So we take that concentration that we're given, multiply that by 1 ml, 1.00 ml. Notice how it's per 1,000 ml. Now this is going to be the concentration. So in other words, we're going to be scratching out our ml here. So we're just left with moles of silver, so or silver plus. Moles of silver plus are also going to cancel out. Then you're just going to be left with moles of silver cyanide. Sorry, I'm missing a 2 there. Okay, and then of course we have to put it back into the overall solution, which is going to be 250 milliliters or 0.250 liters. So that's going to leave us with 4.00 times 10 to the minus 5 molarity of this particular complex. Okay. Now, to actually count or calculate the amount of cyano, we have 0.10 moles. 0.100 moles of cyano group. This is not supposed to be here. This should be 1,000 milliliters as well. Sorry about that. So again, milliliters cancel out, and then you're just going to be left with 2.00 times 10 to the minus 4 moles of CN minus initially available. Okay, so in other words, this is what you're going to be starting off with. Okay, so once we take that amount and figure out the moles of CN minus required to form silver cyanide, we're going to then plug everything out and see how much of the cyano group is going to be free. So eventually we're going to figure out what KF or KD is going to be. Okay, so now we have 1 ml of a different solution, so 0.01 moles of silver, again in 1,000 milliliters or 1 liter, right? Because again, it was expressed at 0.01 moles or molarity. So we're going to get our moles of silver cyanide. Okay. And then we're going to convert that into 2 moles of cyano minus, right? Because we need 2 moles of those to equate to 1 equivalent of silver cyanide. Okay, so now we have 2 moles of CN minus. Okay, so we're just going to be left with moles of CN minus. That calculates out to be 2.00 times 10 to the minus 5 moles of CN minus. Okay, to figure out the moles that are free, so in other words, CN minus, it would go into this particular expression. Moles of free of CN minus is going to be 2.00 times 10 to the minus 4 moles, subtracting from 2.00 times 10 to the minus 5, and then that's going to give you 1.8 times 10 to the minus 4 moles of CN minus. Okay, so with that amount available, dividing that by 0.250 liters, that's going to give you 7.2 times 10 to the minus 4 molarity. Okay, so now as you might expect, we're going to plug this all into an ice chart. So we're going to have our starting concentration of our silver cyanide. We're also going to have our cyano concentration to begin with initially. Okay, so to set this up, this is really a KD, or a K dissociation from silver cyanide over to silver cation and then to cyanoanions. Okay, so we're starting out with 4.00 times 10 to the minus 5 molar, 0 molar of Ag plus presumably, because all of this is going to form in such high abundance, right? Remember that the Kf is going to be 1.0 times 10 to the 21. So it's going to be a high number. Okay. Now, back to the rice chart. So X amount of this is going to go away. X amount of this is going to form. 2 times X amount of this is going to form, right? So if we're to dissociate and form these two different particles, so it has to come from somewhere. Again, it's going to come from the complex. So 4.00 times 10 to the minus 5 molarity minus X is going to give you X amount of Ag plus, and then 7.2 times 10 to the minus 4 molarity of Cn minus plus 2X. Okay. Now, so remember, this is the relationship between these is going to be dissociating. So in other words, it needs to go to the right. So if that's the case, then this should be, instead of 1.0 times 10 to the 21, it should be to the minus 21, because you're taking Kf to the minus 1 or inverse. Okay, so that's going to be equal to X times this particular term. So in other words, we're taking the products, if you will, on the top and then the reactants on the bottom. Now remember that we can approximate, since 4.00 times 10 to the minus 5, which is the concentration we're starting out with, is so much greater than Kd, right? Even if it's 10 to the minus 5, it's way lower or way higher in magnitude than 10 to the minus 21 for Kd. So in other words, we can approximate and scratch out these x's here and make our life a lot easier. So in other words, if we're to solve for x, now all we have to do is just a little bit of algebra to manipulate that and get that to where it's solved for x. So 4.00 times 10 to the minus 5 molar times the Kd, all divided by 7.2 times 10 to the minus 4 molar of Cn minus squared. And that's going to leave you with 7.72 times 10 to the minus 20 molarity of silver plus. So a really, really, really small amount of silver plus that can, as you can recall, combine with Br minus to form precipitate. So essentially 7.72 times 10 to the minus 20 AgBr will form. Well, we'll see about that. Let's take a look back at our KSP of silver bromide. KSP of silver bromide equals, so Ag times Br, concentration. Okay, so that's 5.4 times 10 to the minus 13. Okay, so in other words, that's actually going to be even smaller. So in other words, you won't form any type of product. It won't exceed this particular product of an ion product. So if you're going to take this much and you're going to combine it with 7.72 times 10 to the minus 20 Br, it's still going to remain in solution. It's not going to pop out. So in other words, you're going to see a flask that doesn't have any precipitate form at all. Sorry, that was a huge, long-winded description of what was going on. Sorry about the cat in the background. He was meowing. Whenever he hears my voice, he thinks I'm talking to him. That's just how he rolls. Okay, and that pretty much concludes all of the stuff that's needed to look over for exam 2. I will also have some examples during the review, so don't despair if this all seems kind of crazy. Feel free to ask me any questions during my office hours. Thanks so much. Have a good one.